Hello, and welcome to the OpelX podcast, bringing you candid and open discussions about all things in the power electronics world.
This show is a part of the Open Power Electronics Network. Visit us online at opelex.net. That's opelex.net for show notes, articles, tutorials, and a whole lot more.
My name is Abhijit Kshirsagar. Currently, I am a professor at the Indian Institute of Technology, Dharwad, where I teach and conduct research in the Electrical Engineering Department.
And I am Lalit Patnaik. Currently, I am a fellow at CERN, Geneva, where I work in the Beams department designing power supplies.
Lalit and I were colleagues at the Indian Institute of Science, Bangalore, where we both completed our MTech and PhD degrees in the Power Electronics Group at the Department of Electronic Systems Engineering, DESE.
Over the coming weeks, we will be talking to leading academics, industry professionals, entrepreneurs, and other leaders in power electronics and allied fields. We hope you will find this useful and entertaining. So sit back and enjoy.
Welcome to another episode of the OpelX podcast. Today we are joined by someone with a very different background compared to all our past guests. He is currently a faculty member in mechanical engineering at the Oakland University, Michigan. Please welcome Professor Jonathan Maisonneuve. Welcome, Professor. Can you tell us a little bit about your academic trajectory and training and how you ended up in the Power Electronics and Renewable Energy group at Concordia, even though you appear to be a mechanical engineer?
Well, thank you very much for having me on your program. It's a pleasure to be here. I can give you the short answer, the long answer, because there is a long answer in terms of how I ended up going through several different steps to eventually end up in the Power Electronics and Energy group at Concordia, and how I went on from there. As you said, I'm now in the mechanical engineering department at Oakland University. So the unique trajectory of my training probably will surprise some people. My background includes a bachelor's of environment, which has more an emphasis on biology and chemistry, and then degrees in mechanical and electrical. So that's a pretty unique profile, and the common theme or the common motivation in all of that was always an interest in finding ways to protect the environment. That's something that I've always, I think, I've always wanted to do. I've always been interested in. And so my undergrad degree at McGill University was completed in that specific area, environmental protection and conservation. And I finished that degree, and I thought it was a very good program and very good training. I finished that degree and went to work for a couple years, worked on different conservation projects in Quebec, including with the Nature Conservancy, and had some success there. But what I noticed was that very often we were turning to engineers to develop solutions to problems that we would observe, perhaps in terms of pollution, perhaps in terms of land use and land use management. But very often we were going to engineers, could be civil, could be mechanical, to develop solutions for some of the environmental problems we had. So that was really the motivation for me to go back to university, go back to school, and look at gaining additional expertise, which was in engineering. So that was a difficult transition. Quite, it's quite a different skill set if you talk about the science and engineering. Of course, there are some similarities, but there's also some important differences. That was a process, took some time. So I went back to graduate school at Concordia University in Montreal and got a degree in mechanical engineering, and that led me to get involved in Dr. Pragasan Pillai's research lab. and his the emphasis of that group is electric machines, power electronics.
Mm-hmm.
I had a specific project that I worked on had a little bit more of a mechanical focus, and so I fit into that group well, and that was an enjoyable 4 years. But that's, I guess, how that journey went in terms of going from one degree to the next.
Hey, Jonathan, it's just so fascinating hearing about your career trajectory spanning so many different fields. I was just curious, like when you got interested in renewable and clean energy, even going back further before you started your education, what were some of the early experiences which kind of shaped your interest to go in these kinds of areas of looking at energy and environment?
Yeah, that's a good question, and I think there's a few things that probably motivated me from a young age to be interested in clean energy, sustainable engineering, and one part of it I think would go back to 1998. So I would have been you'll know my age. I would have been 14 at the time. And so, fairly young age, but starting to think a little bit about what I wanted to do and what, careers might interest me. We lived through what's called the North American ice storm. I grew up in Montreal area, and in 1998 we had a massive ice storm. The winters are always pretty bad in Montreal, but this was a unique event. The city and the surrounding areas received a tremendous amount of ice fall, ice rain, freezing rain in a very short amount of time. And the result was that much of the infrastructure was either damaged or destroyed. Including critical power infrastructure. Substations were damaged, transmission lines were down. Even in terms of the civil infrastructure, the bridges, Montreal's an island, there were concerns about weight. And so access to and from the island was limited. All of this led to us living for several days, and in some cases several weeks in some regions. I think in my case we were without power for about 10 days or so. Because most of the heating in the province is electric, that meant for many people no heat.
Wow.
I think Quebec has some of the cheapest electricity rates in North America. So a lot of the heating is electric, and no heating in the winter in that part of the world is a big problem. So I remember us huddled around a fire, trying to keep warm through those days. And somewhere I think that got me to start thinking about critical infrastructure. I think that got me thinking about hybrid power systems, backup power systems, distributed generation. How much we would like to have had, some other source of power. There are, of course, trends for distributed generation and hybrid systems that we see, have seen rapidly develop in the last several years, maybe last decade or so. And so I think this, would be an event, certainly, one of maybe a few, but this would be one that got me thinking about engineering for resilience, engineering for stability, critical infrastructure, and that's continues to be an interest of mine. The engineering systems that I try to develop, one of the motivations is to bring resilience, bring production to the local scale, so that individuals can have some control over critical infrastructure.
One commonality that I would kind of raise here is that while you talk about this ice storm in Quebec in 1998, in the year 1999 in Odisha, where I spent my childhood in the east coast of India, we had a super cyclone, and we also had a power outage of 2 weeks. And it seems like almost a very similar experience at a similar age, and maybe somewhere there also that as well had an influence on me. So yeah, I like to find this commonality.
If I could just add one thing, I think, in some ways, some of the recent pandemic even has maybe caused some people to think about these things as well. If you think even back to especially the early part of the pandemic, February, March of last year, 2020, there were concerns about, having access to certain critical supplies, food. There were some food shortages.
Agree.
Luckily that didn't get to a point of being, devastating, but there were certainly concerns and fears about that. And it does kind of highlight the importance of having some hybrid options and solutions for critical infrastructure.
Abhijit, go ahead. You had a question.
Interesting you mentioned that 98, 99 time frame. 20 years later, I think, just a few months ago, Texas had pretty much the same problem. They had winter storm, they had unusually low temperatures, and pretty much the same problems, right? So power generation was just not equipped to deal with it. And so we had a lot of the same problems, multiple day outages, electric outages, heating was off. And so it seems that, there's still a lot of work that needs to be done before we are at a stage where we can really be free from such issues. So anyway, continuing the conversation, Professor, can you tell us a little bit about what kinds of research problems, more specifically, are you working on now in the energy and renewables sector?
Well, I work at the nexus of water and energy. That means developing systems for clean energy, and it also means developing systems for clean water. The technology that I mostly work with in order to accomplish this is membranes and membrane processes. A very common membrane process that most of your audience, of course, will be familiar with. Their fuel cells for power generation, batteries for energy storage. Membranes are used in many other applications too, though. For water, fairly commonly known process of reverse osmosis is a membrane-based process. So membrane, the characteristic there is you have a material that's selective. That selectivity, that unique property of a material can be used to accomplish many things, allowing certain ions to flow, but not others. That's really the theme of my research. The emphasis is on, in terms of the fundamentals, looking at transport dynamics, fluid mechanics, heat transfer, and how these get expressed in kind of unique processes I'm sure we'll get a chance to get into. But that's, in general, the area of work that I'm in right now.
So are membranes just a fancy word for filter?
Yeah.
Are membranes equivalent to filters?
Yeah, in a lot of ways, yeah. I teach a membranes course here at OU, and I always start by saying, if you've ever made pasta, you boil the noodles, and then you have to remove the water, but you don't want to remove the pasta. So what do you use? You use a filter, you use a strainer, whatever you want to call it. It's the same principle. There are, there are some kind of relatively some important distinctions to make when you get to certain scales.
I see.
But at the base level, yes, it's one of the common strategies for membranes is filtering by particle size. So that is perfectly correct analogy.
So we have these membranes, I guess, inside batteries, inside fuel cells, so many different places that we probably do not think about membranes, especially as electrical engineers, but they are just there inside all of these different things that we use in terms of energy technologies. So I had a follow-up question on something that you have been very actively working on, and that is about osmotic power, where also you use these membrane processes. And could you talk us through what is so fascinating and interesting about osmotic power and your work in this domain?
Sure. So osmotic power is a power generation process. It's a renewable energy process. What it is a energy conversion process that converts salt gradient, energy available in salt gradients, to useful mechanical work, which can be used to drive a turbine and a generator.
Mm-hmm.
If you're a tea drinker, I like tea. And when you make tea, you put, the pouch in the hot, warm water,
Mm-hmm.
and you see, with enough time, you'll see a spontaneous mixing occur.
Uh-huh.
And one of the things that I've learned, I don't know, some people are very serious about tea. One of the things I've learned is I find the tea actually tastes better if you do not mix it, if you allow it to mix spontaneously. But some people may disagree. Anyways, that's not the main point. The point is that you can see that spontaneous action, right? And so there is a chemical potential there when you have a concentration gradient. And everywhere that a river flows into the ocean, you have that same potential. In fact, the head, if you convert a chemical potential to a hydraulic head, you'd be looking at a head of almost 100 meters.
Whoa, okay.
A tremendous waterfall. The potential would be equivalent. And so I got involved in this work when I was in Professor Pilet's lab at Concordia, working with Hydro-Quebec. Hydro-Quebec is the utility company in Quebec. And one of the things Quebec is blessed with is a tremendous capacity in terms of water power. Typically, that's exploited with hydropower, but Hydro-Quebec was interested in exploring the potential of salt gradients. Maybe just to give a little more detail about the process, basically what we do with this osmotic power in an osmotic power plant, what we would do is we'd bring in fresh water, we'd bring in salt water. So you have to have those two inputs. But assuming you have those two inputs, you bring in each of those two streams, and you'll use a membrane that will allow water to pass but not salt. And the outcome will be what's called osmosis. And so the salt water will draw the fresh water up to a point, to equalize the concentrations or the osmotic potential. That osmotic action is spontaneous, and it can occur against the load. Even if you load the draw solution up to a point, you will get basically an expanding volume of pressurized solution, and that has mechanical potential. And so that's the process of what's called osmotic power.
I find your analogy with the waterfall really fascinating, because you could have the river and the ocean almost at the same level in terms of the height, but hidden underneath that, just because of the concentration gradient being so large, you have a waterfall there. It's just that we are not able to see it to the naked eye, that is.
A silent waterfall.
Yeah.
So one thing that I've noticed is that, if you have any salt, right? So if you take, let's say, I've noticed for detergent, if you dissolve detergent in water, it actually becomes warm. So it's actually, exothermic, right? So there's some potential or stored energy that is sort of getting released when the concentration gradient is changing. I know I'm putting it in a very crude, unscientific way, but please feel free to correct me. So what's to prevent, this energy that is stored from becoming heat rather than giving you pressure or giving you usable forms of energy, right?
Yeah, that's a good question. There are reactions that occur, and you can have exothermic reactions, endothermic reactions, and potential energy can be released as heat in that case, as you say. But in fact, when a river flows into the sea, it's not endothermic or exothermic. The proper way to think about it is as entropy, and so you simply have increase of entropy. It's not that heat is necessarily generated. If it is, it's negligible, possibly due to some friction. But really, what we're talking about here is entropy.
My next question is about, you can say it's a little bit selfish, because I'm asking this from the point of view of a power electronics engineer who likes to look at different fields with which we can have interfaces to take energy from and then process it in our electronic circuit. So according to you, what are the good areas or possible areas of synergies between electrical engineers and people like you who work in membrane sciences?
Being in the power electronics and energy research group at Concordia, that was largely our mission and our focus.
Yeah.
My contributions to that project were mostly on the mechanical side in terms of describing the mechanics of this transport process and some of the membrane dynamics. But at the end of the day, the goal is to generate power. And so this type of a power plant would involve significant power electronics for efficient energy conversion. Just like a photovoltaic panel will have some electronics to ensure efficient conversion, and most power systems will include some electronics. This type of system is no different in the sense that there's that need, but it's a unique need. Okay, the dynamics of this system means you have to come up with unique solution in terms of your control strategy. And so in this particular system, I mentioned that the power is generated by osmotic action against a load. Well, the question is, what is that load? If that load is too great, you're actually going to reverse flow. You'll have what's called reverse osmosis. If you apply too much load, too much pressure. Apply no load, and you'll have very rapid flux, but you'll have no power. So you need both. And there are certain transients in this system that require you to take an active approach in terms of developing a solution, as opposed to simply developing a solution at the design stage and it's fixed. You need to have a real-time control approach and solution here. So there are several contributions and collaborations, and those were actually some very nice collaborations that I had at Concordia, working with others to develop power electronics for this type of system.
So you mentioned maximum power point tracking, right? So you want to be able to change some parameter or some characteristic of the system that's harvesting the energy in order to ensure that the maximum possible energy can be harvested. You mentioned, balancing out flow and pressure. And for those of our listeners who've studied a little bit about wind turbines, I think the words you have used are almost identical, right? So if you put too much pressure, then you don't get enough airflow and basically the air just stops. Whereas if you try to allow too much airflow, then you are not getting any power at the output. So those two are very analogous. But in the case of wind, of course, the variable component is the wind speed or the energy in the wind. So what is the variable component or the unknown in an osmotic power system? Is it the salt gradient? Is it something else?
Yeah, that's a good question. That's actually gets to one of the advantages of this type of a renewable power system, in the sense that there are fewer unknowns. There are changes in salt gradients, but they're certainly not as severe as wind. They can largely be predicted, and they occur over fairly large timescales. There are variations, in environmental conditions. Temperature would be another. One of the primary variables at play in this type of system is actually the membrane, and the membrane was called permeability. We characterize the tendency of the material to allow water and salt to transfer as a permeability, and this degrades over time, partly due to fouling, which is a major issue. Impurities in your streams will change this key characteristic. Salt deposition, you'll have some slight salt crystallization, and these can be quite severe. So you can see changes in the permeability, the apparent permeability of up to 50%, and they can be somewhat unpredictable. There are routines that are prescribed, or protocols in terms of cleaning and maintenance, but this is one of the main variables that properly designed maximum power point tracking system will account for. And we've done quite a bit of work there And there's a few, papers we've written on that exact subject, maximum power point tracking, to adjust for this particular variable, which is the main one that you'd anticipate.
So, Professor, could you tell us a little bit about some exciting projects or new problem statements that you've been trying to solve, in addition, of course, to the osmotic power that you have told us in so much detail? Are there any other applications of this technology in some other applications for, let's say, not just power generation, but some other end uses that these technologies can also be applied to?
Yes, in fact, there's many applications. I mentioned probably the most common systems that we would think of for membrane systems with the fuel cells, batteries, reverse osmosis. But there's really a tremendous potential and possibility. We've talked a little bit about making tea. We've talked a little bit about mixing salt and water. You mentioned diluting detergent. Once you start thinking about it, you realize that this type of action occurs all around us in so many different ways. And so anytime you have this mixing with these gradients, you have a potential. Now, can it be harnessed and converted in cost-effective ways? Can it be harnessed effectively? That's, of course, another question. And so we have been developing energy recovery processes for converting the energy from fertilizers to useful power, to useful mechanical work, and so that's one of the areas of innovation that we've been involved in. And to give you an idea of the significance, a typical greenhouse will consume a certain amount of fertilizer and a certain amount of electricity. If you compare the potential of the fertilizer to the electricity, you're looking at something on the order of 10%. 10% of the electricity can come from the potential of fertilizer.
Wow.
Now, there's several challenges with that, which we're working on. But that would be the theoretical limit. So very interesting potential there. And again, it's based on this idea of concentration gradients and making use of them to, in this case, improve the sustainability of food systems.
Is that sort of related to, the heat of ionization or something rather than pure osmosis? Or is it like a combination of the two when you talk about fertilizers?
Yeah, again, there can be, in certain cases, dilution will be exothermic. So it's an important distinction to make. Heat is not a major driver of osmotic action. So if your process is based on exploiting osmosis, heat will have some effect and can be favorable in some cases, but it's not the primary driver. So certain fertilizers are more suitable, have a better potential for certainly osmotic conversion. But osmotic conversion is just one of many options. And for an electric audience, there are electric equivalents to osmosis, including reverse electrodialysis, which is based more on ion transport and charge, generating a potential with transport of charge.
So that's almost like a battery, right?
Exactly. So the concept of a flow battery also, operates on a similar principle. You have, two solutions, and in this case, could be salt water and fresh water, or I'm talking about the farm systems can be a fertilizer solution with their irrigation water.
That's a little bit like an electrochemical cell or a battery, right? You're either putting in energy to move ions, or you're letting ions move and getting energy out of it.
In this particular case, yes. If your energy is converted to heat, then it's lost in terms of this process and how it exploits, and generates work.
So in this case, heat is almost like your enemy, right? So any energy that gets converted into heat is sort of not doing is sort of not harnessable in the osmotic sense. So it's basically not a desirable energy output. Is that correct?
heat doesn't always have to be your enemy, and there's quite a bit of work that we're doing in terms of using waste heat to boost a process.
Right.
Heat can be your friend, doesn't have to be your enemy.
Right.
But in the way you put it, and that's why we're focusing on certain target fertilizers, which are not exothermic in terms of their dilution as our targets for this technology.
So in a way, you are saying that for some of these processes, having a higher temperature is, let us say, in some way better in terms of the efficiency of the process, and hence it's good to have heat produced in some cases.
Not necessarily from the reaction, but if you have an external source of heat, and you can deliver it to the system exactly the way you want, a reaction will occur, and you'll have heat generated. In this case, losing that potential. But I'm talking about if you had a separate source, there can be significant advantages in terms of improving the power density of your processes.
Okay, that's really interesting. Yeah. I mean, again, as an electronics engineer, I'm thinking of what kinds of sensors I would need to put in that system to know exactly when I need to turn on my heater or reduce, throttle it down, throttle it up, that kind of stuff. Really fascinating, yeah.
So interesting. You mentioned that this is for conventional farms, but this is also a good sort of technology for unusual or emerging types of agriculture as well, right? So I believe you have some patents in this area targeted at indoor agriculture, hydroponics, and things like that, warehouse farms. Is that correct?
Correct. In fact, that's, as far as I'm concerned, the target market or the target application for this type of system. These types of controlled indoor plant environments will typically involve quite a bit of precision, quite advanced technology and controls. And so being able to integrate this into the farm is most likely in this type of controlled environment. In fact, that has been the primary source of funding for this project to date has been from NASA, who, in terms of food production in space, food production on the moon, maybe one day on Mars. Of course, there's a renewed push for space exploration in recent years, and longer duration missions will require food production. And so being able to produce food efficiently, being able to recover energy, being able to recover water, because this energy can be used to power electric loads. It can also be used to drive water filtration. There's many ways we can harness this energy. And it also involves efficient use of fertilizer, which is critical to food production in space, where every unit mass has tremendous cost and value. So this is, as far as I'm concerned, the target application would be for controlled plant environments.
Jonathan, that was an interesting point because, when we are talking about space, I mean, every gram counts. And if you're sending up, X grams of fertilizer and you have this hidden energy that was stored in it, making that, fertilizer do some extra work is obviously going to be very, very attractive, especially from the space point of view. But it's got me thinking about something else. This, you mentioned about, you've talked about harnessing energy from salt gradients. But what about going the other way? Can we use energy and create gradients as a means of storage? We do that in batteries. I mean, just sort of thinking about it, it's sort of dawned upon me now talking to you that that's what we are doing in a rechargeable battery, right? We are using energy to create a gradient of ions. But can we do that in other ways using membranes?
Absolutely, and that is a very interesting line of work and a line of thought. There's many concepts that, not that many, but there are a few concepts that have been proposed along those lines. I'll give you one example, which is referred to as the osmotic heat engine. In this type of process, you would not have I talked about using a river and the sea, but you can imagine a closed loop system with any type of working fluid. Doesn't have to be salt. You could have any type of working fluid that would be regenerated when energy is available. Could be from a solar, could be from wind, could be from any type of source, could be thermal or other, using that energy when it's available to separate, and then when the energy is needed, running it in reverse and mixing.
Yeah.
And that gets to one of the kind of fundamental concepts in the membrane science, is that you can manage a separation process just as you can manage a mixing process. And I like to give the analogy of a generator and a motor. And the same way that you'll have a group that will do work on motors, probably the work will include some generator applications, and the electric machine can be run one way or the other. And so it is with these membrane processes. And so, my group, we do work on energy, power generation, but we also do work on water treatment and water purification, simply by running a lot of these systems the opposite way. When you talk about energy storage, that's an interesting kind of example of how these things can come together.
Jonathan, when I see all these different, let's say, range of projects where you have essentially some physical processes that you are trying to look at and usefully harness energy from them, or address water problem or food problem. So you are tackling so many different kinds of problems, and it becomes quite interdisciplinary. And I was just trying to think how one person can possibly handle so many different kinds of fields. And it kind of reminded me of, let's say, a quote from Professor Omanand, which I will just read out from the first episode where we recorded an interview with him. So he says in that episode, if you look at physics as the mother of all the inanimate sciences, you are domain free. You lose the fear of domains, and that is what an engineer should do in order to solve problems.
Well, that's a great quote, and I should ask you for that because I would like to use it.
Yeah, sure.
I think that's part of the fun, actually, of being an engineer, of having some understanding of fundamentals. Is in a lot of ways there is a freedom there, and it's an exciting thing to be able to make connections between fields and be able to innovate as you make these connections.
Yep.
And so I totally agree with that quote, and in fact I think I'd like to use it at some point, so I'll have to get that from you.
In your lectures.
Exactly. Because I always try in my classes to emphasize that with the students. We're talking about fluids. I'll make analogies to heat transfer. I'll make analogies to circuits. The more we can connect and expand our understanding, it allows for innovation. It allows for collaboration. I think there's so many advantages to making those connections.
Yeah, definitely. Yeah, 100% agree.
Interesting. So in all our conversation, we've covered a lot of multidisciplinary or interdisciplinary problems. One of the questions that I often get is students who are getting into the field, they want to focus on, let's say, only electrical or only mechanical. They don't get an opportunity to explore these multidisciplinary areas. So for students who are joining your group, or for prospective students who you expect should get into these problems, can you give some pointers, some advice about how these students should prepare themselves, or what are some resources that they can use to make sure that they are better prepared to tackle problems like these in future, in their academic or professional careers?
Yeah, that's a good question. I think for students, it's of course a journey. You get into your university program. Personally, I think one of the keys is to really try your best to master some of the mathematics. Mathematics being a language, and if you look, we talked about the interdisciplinary nature of this work. Being able to express different phenomena mathematically is really a key, because it connects different fields via a common language. That being said, I think the other thing is to not be afraid. Not be afraid of of other fields. Of course, you have respect. You have certain expertise. If you're trained one way, you have your strengths. But with a certain amount of application, you can translate what you know from one field to another, and it takes some effort. But if you can become comfortable in your math and you can become comfortable in your field, those opportunities will open up. So for a student that's trying to make a decision, I think it's important to remember that it's not one decision. You're going to have many opportunities through your university career. You're going to have many opportunities through your working career. You're never going to stop learning, and to keep that desire to want to keep learning also is I think a key part of any type of success.
Yes, Jonathan, that is just such an apt advice. Thank you so much. And I guess although we would want to go on and on in this conversation, we have to call it a day, I guess. So I would just like to close by thanking you, first of all, for teaching us, electronics engineers largely here, teaching us something about all these membrane processes. And these are kind of hidden pockets of energy in nature that sometimes we might ignore. And quite often in the sustainable energy landscape, the limelight happens to be on solar photovoltaics, wind, maybe geothermal, but often we do not think about these kinds of hidden pockets of energy that you brought out to us to kind of open our horizons to these kinds of places. So I would like to thank you again for that and for sharing your expertise and your time.
Well, it's been my pleasure. Thank you so much for the invitation.
Our pleasure.
Before we part, where can our listeners find you on the internet? Do you have social media profiles? Do you have web pages, or do you have a web presence?
Yeah, the best way to find me is just by if you Google Prof Maisonneuve, should be normally the first result that will come up. There's a link to my webpage with all contact information and some information about projects and research and different activities that I'm engaged in. So that's the best way to learn more and to get in touch.
Excellent. Yeah. We will add the links in our show notes so our listeners will know where they can contact you.
Perfect.
And thank you again, Jonathan.
Okay. Thank you so much for the invitation.
Thanks again. Bye-bye.
Thank you very much. Bye-bye.
The OpelX podcast is a part of the OpelX project. You can follow us on Twitter. We are at OpelXNet. You can email us at opelxpodcast@gmail.com for feedback, questions, comments, and suggestions. This podcast is hosted by me, Abhijit Shirsagar, and Lalit Patnaik. Mixing and sound engineering